Hi, so if you're watching this video, presumably you have already watched day 2 of our Polynomial Functors course. We just wanted to go over some portions of the video again where the video actually cut out. So we know that that might have been a little confusing, so we're going to just go over a little bit of each part that was cut out right here. The first thing was we looked at this state diagram. I called these states rooms, but usually we'll call them states. And we drew the sort of trees that represented the futures from each of these states. So the first one we did was with the moat. So if we start from the moat, denoted by this node labeled M, we can go either left or right. If we go left, we end up at the tower. If we go right, we end up at the sea. Now, starting from the tower, we can also go either left or right, which leads us either to the dungeon or the beach. From the dungeon, we can't actually go anywhere, so this node corresponding to the dungeon actually has no children, whereas the node corresponding to the beach, we can go right, but we can't go left, so it just goes right like this. And similarly, from the sea, we can also go right, but we actually end up right back at the sea. And so if we started from the sea, we could actually just keep going right, and this graph would just keep going on forever. And we have another copy of the sea down here, so this would also just keep going right forever. We can also do the same thing if we started from the cottage. We can only go left from the cottage, which takes us to the beach, from which we can only go right. So once again, we have this infinite line going rightward that way. Separate these a little bit because these are two separate trees. And finally, if we wanted to represent what happens at heaven, then it's just a single node without any children, because you can neither go left nor right from heaven. Now you may be asking, where are the future trees for the tower and the dungeon and the beach and the sea? But we've already actually drawn all of those just as subtrees of the trees we've already drawn. So for example, didn't mean to erase that. For example, the future tree for the tower is just this subtree that I've highlighted here. Okay, and so all of these possible trees, so all of these possible binary trees, by which we mean trees where each node either has a left child or a right child, or both, or neither. All of these trees form the objects of a category, and we'll talk more about this category on day 9, but for now you can know that the morphisms of this category are given by rooted paths of these trees. So for example, if we start from this object, this large tree here, one of the morphisms coming out of this tree is represented by the rooted path that starts from here, goes left, and then goes right. And so that path is one of the morphisms out of this tree, and the codomain of that morphism turns out to be the subtree of this tree, whose root is the end of the rooted path. And so you can see how each morphism has a codomain, or you can find out what the codomain of the morphism is like this. And you can think about how these categories compose, or you can wait till day 9 for us to delve into this further. And finally, the last thing I did that got kind of cut out was I just labeled some of these objects that show up here. One thing to clarify is that these trees, we're thinking of the objects of this tree as, or the objects of this category as unlabeled trees. So if we ignore these labels, for example, the tree that comes out of the beach is actually the same, has the same shape. It's the exact same tree as the one that comes out of the sea. So we can label all of these trees without repeating our labels. and I believe we called this entire tree, and we're just going to draw write down the labels at the roots of the trees that we're labeling. So this giant tree we called W. We called this giant tree V. We called this tree down here W. We called this tree X. We called all of these rightward rays, we called them Y. So every one of these is a Y. And finally, we called the dead ends that show up twice here, these one-note trees, we call them Z. It shows up for both the dungeon and heaven. And there we go. Alright, so now the parts that got, unfortunately, cut out a little bit towards the end of the video, I guess there were sort of 2 or 3 things. First off, the way we defined the parallel product is if we say, if we take the polynomial, which is just a monomial, ay to the b, and we tensor it with cy to the d, we define that as taking both the product of the 2 coefficients, both a and c, as well as the product of the exponents b and d, which, as you can see, contrasts from taking just the product of these 2 monomials, where we would take still the product of a and c, but we would actually add the exponents b and d. Then the other product we introduced was the composition product, which we will go into more detail on day 6. But by composition, we just literally mean composing the 2 polynomials together as if they were functions or functors. So for example, if we have 2y squared composed with y cubed plus 1, well, that would just be replacing the y up here with whatever shows up here. So that's going to be 2 times y cubed plus 1 squared. And you could expand that out to figure out exactly what polynomial that would be. Finally, towards the end, in response to some discussion, we were talking about exactly how you could visualize products in terms of making decisions and delegating decisions. And so the key thing we know about a product is that if we have a morphism from some polynomial r into p and some other morphism into q, well, that's just equivalent to a morphism into the product of p and q. And so we can think of a delegation of decisions. If R wants to find out, or if someone has as their menu the polynomial R, and they would like to delegate one of their decisions to both someone with the menu P and someone with the menu Q, each of these parties would then send back an option of the decisions that they got in order to specify an option of R. And that's kind of equivalent to thinking about here, R would send their decision to actually a pair of decisions, because the decisions of P times Q are just pairs, and P times Q here would send back, they could either send back one of the options that corresponded to an option of P, which would correspond to some option for R up here, or they could send back an option of Q's, and they would correspond to some other, or maybe the same option of R up here. Yeah, so hopefully that clears up anything that was confusing due to the video cutting out, and we hope to see you for class on day 3. Thank you.